In this lecture, we are going to study the performance of the CMOS inverter, the dynamic behavior. So basically, we will derive the resistances and capacitances of the NMOS and PMOS transistors in a CMOS inverter. And based on that, we will calculate the propagation delay. So with that goal in mind, let us proceed with the lecture. First, we will compute the capacitances and resistances, and then we will calculate the propagation delay. The propagation delay of a CMOS inverter is determined by the time it takes to charge and discharge the load capacitor through the NMOS and PMOS transistors. We know that when the input is high, the NMOS is conducting and the PMOS is open. And when the input is low, the PMOS is conducting and the NMOS is open. And then we have a capacitance, CL, which we are going to derive. It charges through the PMOS when the input is low, and it discharges through the NMOS to ground when the input is high. So the goal is to achieve as small capacitance CL as possible. So we are going to study the major components of the load capacitance of a CMOS inverter for that purpose, and we will perform in-depth analysis of the propagation delay of a CMOS inverter. Here is how we calculate the performance of a CMOS inverter. It's equal to propagation delay from low to high transition plus propagation delay from high to low transition divided by 2. Here is our input signal plotted versus time, and here is our output signal plotted versus time. And for the propagation delay, we are mostly concerned with the 50% amplitude points. So the propagation delay from high to low is between these two 50% amplitude points. We call it propagation delay from high to low because here our output is transitioning from high to low. And then our propagation delay from low to high runs from between these 2 points. Once again, we call it propagation delay low to high because our output is transitioning from low to high. We can model the propagation delay of an inverter with the help of an RC network, because we know that both NMOS and PMOS transistors have particular resistances and they have particular capacitances as well. And their product gives us the RC time constant. And we also derived in one of the previous lectures that the time it takes to reach the 50% point is natural log of 2 times tau, or is equal to 0.69 times tau. Before calculating the inverter capacitances, let us review our concept of the MOS capacitance, of the metal oxide semiconductor capacitance. We already covered this topic in detail in chapter number 3, but let us review it for the sake of refreshing our mind. Here is an NMOS structure where we have a gate, a silicon dioxide insulator, then we got a substrate. For the NMOS structure, the substrate is P-type and the drain and source would be N-type. So basically we have a capacitance between the gate and the bulk under cutoff conditions, because under cutoff there is no channel. So a capacitance is formed between the gate and the channel. In linear mode of operation, we know that there would be a uniform channel running between the source and the drain. And here is another pictorial depiction of that. So in linear mode of operation, this capacitance is distributed between the gate and the drain, called the gate to drain channel capacitance. and between the gate and the source, called the gate to source channel capacitance. So basically it's distributed over two components in a linear, or we can also call it the resistive mode of operation. In saturation mode, we know that we have a pinch off point where we see that our channel is now shifted from the drain towards the source. It's not connected to the drain anymore. And since the channel is connected just to the source in case of saturation, so in saturation we only have the gate to source channel capacitance. We don't have gate to drain channel capacitance in saturation. Other components of the MOS channel capacitances are the overlap capacitances. We know that there is a slight overlap between the gate and the drain over here, and also there is a slight overlap between the gate and the source as well. And there is an insulator between the gate and the drain, and an insulator between the gate and the source as well. So these form the gate to drain overlap capacitance and the gate to source overlap capacitance. And these overlap capacitances are actually independent of the mode of operation of a transistor. So they are going to stay the same in cutoff, resistive, and saturation mode. Another capacitance associated with a MOS transistor is the diffusion capacitance, or we can also call it the junction capacitance. We know that there is a p-n junction over here. The p layer comes from the substrate and the n layer comes from the drain. And whenever we have a p-n junction, there is uncovering of positive and negative charges. And this uncovering of positive and negative charges actually results in a capacitance over here at this p-n junction. And similarly, we have a depletion or diffusion capacitance over here as well for the p-n junction on this side. This diffusion or junction capacitance has two components. It has a bottom plate capacitance formed by this p-n junction on both the drain and the source side, and it has a sidewall capacitance. This drain region over here has three sidewalls: the front sidewall, this sidewall, and the back sidewall. We don't count this left sidewall because it is connected to the channel. Why do we account for a different sidewall capacitance? Why don't we combine it with the bottom plate capacitance? Is because there is an implant region around the drain and the source. It's a P plus implant region. So in fact, it forms on the sidewalls, it actually forms a P plus N plus junction. So its capacitance is going to be different as compared to the bottom plate capacitance. So overall, these are all the capacitances associated with a metal oxide semiconductor structure. Then let us consider each one of them one by one. First, let us consider the gate overlap capacitance. Here is a layout of the gate overlap capacitance. This orangish region over here represents the polysilicon gate, and it has a slight overlap with the drain region and a slight overlap with the source region. This spacing is XD over here. To calculate this overlap capacitance is really easy. We just need to multiply the area of this overlap region, which is XD times W, with C oxide, where C oxide is equal to permittivity of the oxide divided by thickness of the oxide. Its unit is farad per centimeter square. So since we need this overlap capacitance in farads, we multiply C oxide with the area of the overlap region, giving us the capacitance in farads. Or we can also use this formula in which we have C overlap, the overlap capacitance, a technology parameter. We just need to multiply it with the width of the channel, and it gives us this gate overlap capacitance. Now let us talk about the channel capacitance. and try to fill out this table. In cutoff region, we just have the gate to bulk capacitance, which we already discussed. The gate to source channel capacitance and gate to drain channel capacitances would be 0. So in cutoff region, we have the gate to bulk channel capacitance plus 2 times the overlap capacitance. Why 2 times? Because we have to account for both the drain and the source regions. And as I told you, this overlap capacitance would be the same in cutoff, resistive, and also in saturation region, as you can see over here. In resistive mode of operation, the gate to bulk channel capacitance is 0, and this capacitance is distributed equally over the gate to source and the gate to drain channel capacitance. So adding up these two and then add the overlap capacitances to it for resistive mode of operation. In saturation, the gate to bulk channel capacitance is 0. Similarly, the gate to drain channel capacitance is 0. We just have to account for the gate to channel capacitance and add it with the overlap capacitance. Now that covers the gate capacitances. Let us talk about the diffusion capacitances now. The diffusion has 2 components, the bottom plate capacitance and the sidewall capacitances. The bottom plate capacitance can be calculated using this simple formula, which comes from the p-n junction diode theory, already discussed in one of the previous lectures. Simple and straightforward formula, involves acceptor doping and donor doping. Acceptor and donor dopings are the dopings of the source or the drain, but here we have mentioned the source side. So the doping of the source and of the substrate. Phi is the built-in potential. We can easily calculate it using this simple formula. So it's going to give you the junction capacitance. And then the bottom plate capacitance, this gives us capacitance per unit area in farad per meter square or in farad per centimeter square. So just multiply it with the area of this bottom plate, gives you capacitance in farads. Here is an example based on that as well. For the sidewall capacitance, we have these 3 sidewalls. This sidewall has a length of Ls, the length of the side of the source, plus width of the channel, and then another sidewall. So 2 times Ls plus W. And we got to multiply it with a parameter called CJSW, which is a technology parameter for the sidewalls. Its unit is in farad per meters. Multiply it with this parameter of the source. It gives us capacitance in farads, or it gives us the sidewall capacitance. We don't, as already discussed, we don't take into account this side for the sidewall capacitance because this side is connected to the channel. So then we combine the bottom plate capacitance and the sidewall capacitance. And here we have listed all the capacitances for the metal oxide semiconductor. And previously we talked about this example as well. The formulas are already given, so I don't want to go over this example once again. Simple and straightforward. Our main goal today is to discuss the inverter capacitances. Now, the transistor capacitances actually involved a lot of things: the gate to channel capacitances, the overlap capacitances, the diffusion capacitance of the bottom plate, and diffusion capacitance of the sidewall. But so far we were talking about just one transistor, and now we want to talk about a cascade of 2 inverters, where each inverter has an NMOS and it has a PMOS as well. So manual calculation of all these capacitances would be extremely challenging. So what we do is we try to lump together all these capacitances into a single capacitance at the output between V out and ground. Here is our circuit diagram of the two inverters in cascade. Here is inverter 1 corresponding to this, and here is inverter 2 corresponding to this. They are in cascade. Each inverter has an NMOS and a PMOS. This inverter also has an NMOS and a PMOS. We call this NMOS transistor 1. We call this PMOS transistor 2. We call this NMOS transistor 3, and we call this PMOS transistor 4. Now, we are mainly interested in the capacitance at V out at this point over here. And we know, how do we label the sources and drains of these transistors? I already told you. Here is the gate of the NMOS, here is the gate of the PMOS. The source of the NMOS is connected to ground, and the drain of the NMOS is connected to V out. Similarly, the drain of the PMOS is connected to V out, and the source of the PMOS is connected to VDD. And so we are concerned with all the capacitances connected to V out over here. In this case, like for example, we have the gate to drain capacitance of this NMOS and the gate to drain capacitance of this PMOS. Similarly, the diffusion capacitance of the NMOS and diffusion capacitance of the PMOS. Similarly, the wiring capacitance at the output. And then we are also concerned with the fan-in capacitances over here for the second inverter. The gate capacitances for the NMOS and for the PMOS. But actually, here we account for the gate to drain overlap capacitance of the NMOS and for the gate to drain capacitance of the PMOS. But we don't account for the gate to source channel capacitances and the gate to drain channel capacitances and the gate to bulk capacitances. There is a particular reason for that. The reason is that we are in terms of propagation delay, we are only concerned with the 50% points. And in this transition region, we know that our transistors are both NMOS and PMOS are either in cutoff or they are in saturation. And we know that in cutoff and also in saturation, our gate to drain channel capacitance is 0. And since over here we are primarily concerned with the drain capacitance of the NMOS and drain capacitance of the PMOS at the output, and we know that in saturation and cutoff we don't have the gate to drain channel capacitance. So we are going to ignore that. We only consider the gate to drain overlap capacitance for the NMOS and the gate to drain overlap capacitance for the PMOS, represented by CGD1 and CGD2. Here we have lumped them into just CGD1, 2, but we have both of them. And similarly, as I'll discuss, there would be diffusion capacitance of the NMOS, including both the bottom plate capacitance and the sidewall capacitance, and the diffusion capacitance of the PMOS, including both the sidewall capacitance and the bottom plate capacitance. Similarly, the wiring capacitance, and we got to calculate the gate capacitances of this transistor. This includes the channel capacitance and the overlap capacitances. And similarly, the gate capacitance of this transistor, which also includes the channel capacitance and the overlap capacitances. So let us proceed further. Here is the switch model for the dynamic behavior of the CMOS. So we know that from low to high transition, when the input is low, the PMOS is conducting and the NMOS is open. So in this case, our Vout is connected to VDD through resistance P, which is the resistance of the PMOS. And this capacitor over here, CL, charges through VDD. Similarly, for high to low transition, when the input is high, the PMOS is open and the NMOS is conducting. So the NMOS will have a certain resistance in this case. And in this case, this capacitor discharges through this resistance Rn to the ground. For calculating the capacitances of the inverter in Cascade, we already discussed different components. As we already discussed that it has this component CGD1, the gate to drain overlap capacitance. So we got to calculate that, the gate to drain overlap capacitance. Similarly, CGD2, the gate to drain overlap capacitance of the PMOS, the gate to drain overlap capacitance of the PMOS. So we need to calculate that as well. Then we need to calculate the diffusion capacitance of the NMOS. The diffusion capacitance of this NMOS. And this further has two components. This has a bottom plate capacitance and a side wall capacitance. Similarly, let's go back to the table once again. And then we need, so this has the bottom plate capacitance plus the side wall capacitance. Similarly, we need to calculate the diffusion capacitance of the PMOS. Diffusion capacitance of the PMOS. Once again, this has two components. The bottom plate capacitance plus the side wall capacitance. And then we need to calculate the gate capacitance, capacitances of the fan-in. So these are the fan-in transistors. The gate capacitance of the NMOS needs to be calculated and the gate capacitance of the PMOS needs to be calculated. And these gate capacitances have the channel capacitance component and also the overlap capacitance components for the drain and for the source for both cases. The wiring capacitance is generally going to be given in your problems. So this capacitance, the gate to drain overlap capacitance and also the gate to for the NMOS and the gate to drain overlap capacitance for the PMOS is going to be the same for high to low transition and from low to high transition as well. Similarly, we will talk about these two a little bit later. The gate capacitances would also be equal for high to low and low to high transitions. But the drain, the diffusion capacitances of the NMOS and also the PMOS involving both bottom plate capacitance and the side wall capacitance for both these, for these two, they depend on the voltage. So their values are going to be different for high to low transition and for low to high transitions. And because of these difference in these two, the overall capacitance, the total capacitance is going to be different for high to low transition and for low to high transition. Let us tackle each one of these capacitances one by one now. So as I already told you that we have a capacitance for the NMOS, we call it the gate to drain overlap capacitance, and then another capacitance, the gate to drain overlap capacitance for transistor 2. It can be lumped into one capacitance. But this is a floating capacitance between the input and output, and we need to convert it into a capacitance between the output and ground. For that purpose, we can seek the help of this Miller effect, which states that during low to high and high to low transition, the terminals of the gate to drain capacitor are actually moving in opposite directions. So the voltage changed over the floating capacitor is twice the actual voltage swing, and because of that, this capacitance to ground must be twice as large as the floating capacitance, or this CGD is equal to twice this floating capacitance. So this solves our problems, and in the table it's given that this gate to drain overlap capacitance for the NMOS is equal to 2 times the gate to drain overlap capacitance times W, the width of the transistor. And it's given in one of the table, like slide number 32 is really crucial for you. The overlap capacitance for the NMOS, its value is given. Similarly, the overlap capacitance for the PMOS, its value is also given for 0.25 micrometer CMOS processes. So you can just pick these values and put them into this formula to calculate the gate to drain overlap capacitance for the NMOS and for the PMOS. Now let us focus on the diffusion capacitances for the NMOS and for the PMOS. Now, if the voltage is 0, it's really simple and straightforward. We can easily calculate the junction capacitance, and here the built-in potential can be calculated using this formula. But generally, we have input and output signals in these circuits. So we got voltages, and whenever a voltage is involved, this capacitance, this diffusion capacitance, is actually a nonlinear function of the voltage then. In order to linearify it, we multiply the junction capacitance with a parameter called K equivalent, where K equivalent can be calculated using this equation. In this equation, V high and V low are our supply voltages based on whether it's low to high transition or high to low transition. Phi is the potential, and the value of phi are also given in this table for both the bottom plate and for the sidewall capacitances as well. Similarly, the parameter M, its values for 0.25 micrometer CMOS technology is also given for the bottom plate and for the sidewall capacitances as well. So if we know the value of, we already know the values of phi and M from the table, and if we know if we got low to high or high to low transition for either the NMOS or PMOS, we can easily calculate the value of K equivalent. So let us try to calculate the values of K equivalent initially for NMOS for high to low transition. We know that for high to low transition at the output, talking about the 50% points, we are transitioning from 2.5 volts to 1.25 volts. So our high voltage is 2.5 and our low voltage is 1.25. We have this minus sign because the drain and the sources are reverse biased. Because the drain is reverse biased, right? So putting in these values, 2.5 and 1.25 into this equation, and we can plug in the values of phi and M for the NMOS from this table, the value of phi for the NMOS from here. So using putting in these values and using this equation, we can calculate it for the bottom plate, and we can calculate K equivalent for the sidewall as well for high to low transition. Similarly, for low to high transition, let us go back to this plot. For low to high transition, once again we are talking about the 50% points. So we are transitioning from 0 to 1.25 volts, right? from 0 to 1.25. Once again, it's reverse biased, so we use minus 1.25. And pick the corresponding M and phi values from slide number 32. M and phi values for the NMOS from slide number 32. So using that, we can calculate its values for low to high transitions as well. So here are our values for K equivalent for the bottom plate and also for the sidewall. And similarly, we can perform the same calculations for PMOS as well, for high to low transition and for low to high transition. So the calculations for capacitances are extremely demanding, time demanding especially. So what I'm going to do is that in your exam problems, I am going to mention the values of K equivalent for the bottom plate and sidewall for both NMOS and PMOS for high to low and low to high transitions. I'm not going to require you to calculate these values in your exam because we need to focus on more important things. Now finally, the fan-in capacitances over here. CG3 and CG4, we already got formulas for them. Just pick the parameters from the table given in slide number 32, put in all the values, and you can easily calculate the fan-out, not fan-in, the fan-out capacitances as well. And put in these values into the table. Now, I want to proceed towards an example for solving the capacitances, but before that, we need to understand a few terminologies. We got VLSI design rules. So, the circuit designers, they are actually interested in high circuit density. The process engineers, on the other hand, they care more about yield and repeatability of reliability of the process. So there is always a compromise between the two. And for that compromise, a set of design rules are required, like what is the length of this channel going to be? What should be the width of the polysilicon? What should be the width of the metal interconnects, and about the silicon dioxide and everything else? So for that purpose, we define a set of rules. We already know about the minimum line width. The minimum line width or the minimum feature size of a transistor is the distance between the drain and the source, denoted with L. Here is a cross-sectional view of our structure, and here is a layout view. So here we also define different layers. We actually associate different colors to different layers. Like for example, polysilicon, here the color is kind of pinkish, but it's actually orangish color is associated to polysilicon. There are two types of design rules primarily. The first one is industry standard, or we can call it micron rule. In this, all the device dimensions are mentioned in terms of absolute dimensions, like in micrometers or in nanometers. The second one is scalable design rule. In scalable design rule, it's based on lambda. It's developed by Mead and Conway, and in this, all the device dimensions are expressed in terms of a scalable parameter, which is called lambda. But what is lambda? Lambda is equal to L divided by 2. What is L? The minimum feature size, the technology node, the spacing between the drain and the source. So lambda is equal to half the technology node, or in other words, you can say that this minimum feature size is equal to 2 times lambda. So all the dimensions are actually represented in terms of lambda. There are different layers in our CMOS design: substrates and diffusion regions, polysilicon layers, metal interconnects, contacts, and via layers, and we associate different colors to them. And also we define some scalable design rules that the minimum width of the transistor should be this lambda, and the minimum spacing should be this much. Like for example, in case of polysilicon, the minimum width should be 2 lambda. So similarly, there are two different design rules For example, the minimum width for transistors should be 3 lambda and the minimum length or L should be equal to 2 lambda. Now here is our cascaded CMOS inverter once again. Here is the circuit diagram of that. But in terms of layout, we actually represent it like this, in which we have a ground railing and a supply railing. The NMOS over here has a source which is connected to the ground. So this region over here actually represents the source of the NMOS. And this region represents the drain of the NMOS. Then we have a polysilicon layer. This side over here represents the length of the transistor. And this side represents the width of the NMOS transistor. Similarly, this polysilicon then runs over the PMOS as well, where this side is the length of the PMOS and this side is the width of the PMOS. The source of the PMOS is connected to VDD and the drain of the PMOS is connected to Vout. Similarly, the source of the NMOS is connected to ground and the drain of the NMOS is connected to Vout. Another point that we can actually observe from this figure is that, and we already know, that the width of the PMOS is generally larger as compared to the width of the here is the width of the PMOS. The width of the PMOS is generally larger as compared to the width of the NMOS. We already discussed it from the perspective of where the threshold voltage should be, and also here we are going to know how it affects the performance of the CMOS inverter. But anyhow, let's move to our example here. In fact, the next figure. So here is our example, and we are required to calculate the capacitances of this inverter for low to high and high to low transition, and we are also required to calculate the propagation delay of this inverter for low to high and high to low transition. For the sake of calculating the capacitances, we know that we need to fill out this table, right? Where this is easy, just pick the values from the table in slide number 32 and fill it up. These are also easy, but this part, I mean the K equivalent, I'm going to give you the values. The junction capacitance can also be inserted for the sidewall and for the bottom plate as well from the table given in slide number 32. But a high portion of your time would be spent on the calculation of the area of the drain of the NMOS and perimeter of the drain of the NMOS, because for the sidewall we need to calculate the perimeter, and then area of the drain of the PMOS and the perimeter of the drain of the PMOS. So let us first focus on calculating the areas of the drains of the NMOS and PMOS and the perimeters of the drains of the NMOS and PMOS. Even before that, let us identify the PMOS and NMOS in this layout diagram. Here is our NMOS. As I already told you that this is the source of the NMOS. As I already told you that the source of the NMOS would be connected to the ground railing. And this is the drain of the NMOS. The drain of the NMOS would be connected to Vout. Similarly, here is our PMOS. And this is the drain region of the PMOS. Similarly, this is the source region of the PMOS. In our calculations, we need to calculate the area of the drain of the NMOS and perimeter of the drain of the NMOS. And similarly, area of the drain of the PMOS and perimeter of the drain of the PMOS. So let us focus on that. And also for this NMOS, the width to length ratio is also given. The width is 3 lambda and the length is 2 lambda. or the length is equal to 0.25 micrometers. So if the length is this, lambda is this divided by 2. So our lambda is 0.125. So please note this point. Our lambda in this case is 0.125. Length is 2 lambda. It means 0.25 micrometers. Width is 3 lambda. It means 0.375 micrometers for the NMOS. This is the length of the NMOS and this is the width of the NMOS. Similarly for the PMOS, our length once again is 2 lambda, 0.25 micrometers, but the width given over here in this example is 9 lambda. So 9 into 0.125 is 1.125 micrometers is the width of this PMOS. And in our calculations for capacitances, we need the areas of the drain of the two and the parameters of the drain of the two. We are not going to be concerned with the areas and parameters of the sources. Just focus on the areas and parameters of the drains. So let us first calculate the area of the drain of the NMOS. Now, this pad over here is also part of the NMOS. And according to the design rule, this should have a dimension of 4 lambda. So then we can divide this into two regions. First, this square region pad, which has an area of 4 lambda into 4 lambda, 16 lambda square. And then this rectangular part, where this side is 3 lambda and this side is 1 lambda. So the area of this is 3 lambda square. So 16 plus 3 lambda square is 19 lambda square, which means 19 into 0.125 into 0.125. It gives us this value. Now let us focus on the perimeter of this drain of the NMOS. Now this side is 1 lambda plus 4 lambda becomes 5 lambda plus 4 lambda becomes 9 lambda plus 4 lambda becomes 13 lambda plus 1 lambda 14 lambda plus 1 lambda 15 lambda. So the perimeter of the drain of the NMOS is 15 lambda. 15 multiplied by 0.125 comes out to be 1.875 micrometers. Now let us focus on the area of the drain of the NMOS. This side is 4 lambda plus 1 lambda, 5 lambda. This side we know is 9 lambda. So 9 into 5 is 45 lambda square. So the area of the drain of the PMOS is 45 lambda square. 45 into 0.125 into 0.125 gives us a value of 0.7 micrometer square. How about the perimeter of this region? Perimeter is 5 lambda plus 9 lambda plus 5 lambda. 10 plus 9, 19 lambda. So 19 lambda, 19 into 0.125, 2.375 micrometers. And I told you we don't count this side because it is connected to the channel. Similarly, over here we don't count this side in terms of perimeter because this is connected to the channel. Now that we know the areas of the drains of the NMOS and the PMOS and also perimeters of the drains of the NMOS and PMOS, the rest of them, the rest of the values you can pick from the table given in slide number 32. From this table over here. And the K equivalent values are already given in the previous slides. So put in all values, you can calculate all the associated capacitances for the high to low and low to high transitions. So this is the total high to low transition capacitance, and this is the total low to high transition capacitance. As I told you that these overlap capacitances would be equal for both high to low and low to high transitions. This would be the same as well. The gate capacitances are the same as well for high to low and low to high transition. The wiring capacitance is the same. The only change you see is in the diffusion capacitances for high to low and low to high transitions because the K equivalent value in all these cases is not the same. Now In order to calculate the propagation delay, we need two components. We need capacitance and we need to know the resistance as well. We already covered the capacitance part. Now let us calculate the resistance part. Here is a formula for calculating the resistance, and it's a complicated one. But for 0.25 micrometer CMOS process, here are the NMOS and PMOS resistances versus the supply voltage. And mostly we are going to focus on 2.5 volts. So we are primarily concerned with an NMOS resistance of 13 kilo ohm and PMOS resistance of 31 kilo ohm. And this is for a width to length ratio of 1. These values are for W divided by L ratio of 1. If we have a different width to length ratio, then we need to divide these values by that particular ratio. Propagation delay for low to high transition can be calculated using this formula, and similarly for high to low transition, where we are concerned with the resistance of the NMOS involves this formula. Or overall you can simplify it into this formula as well. But first, how do you calculate the resistances? So overall we got this formula for propagation delay from high to low, 0.69 times resistance of the NMOS times capacitance involved from high to low transition. So if you see over here, this NMOS is involved in high to low transition. So we need to use the corresponding capacitance of high to low transition. The corresponding capacitance from high to low transition came out to be 6.1, and for low to high it came out to be 6.0. So moving forward, for high to low transition, we need to use the NMOS resistance and we need to use the high to low transition capacitance. For the resistance part, as I told you, that it can be figured out from the table over here. To be using 2.5 volts for the NMOS, so 13 kilo ohm. But our width to length ratio from this figure over here is 3 divided by 2, 1.5 for the NMOS and 4.5 for the PMOS. So we need to use the right ratios as well. So for the NMOS, divide this value by 1.5, and for the PMOS, divide this value by 4.5. And we get the propagation delay from high to low transition and also for low to high transition, and take the average for the overall propagation delay. Here is our propagation delay plotted versus the supply voltage. From the trend, we see that the propagation delay decreases with an increase in the supply voltage. This is opposite what we found in the gain for gain versus supply voltage. For that, we found that the gain actually increases with a decrease in the supply voltage, or the gain actually deteriorates with the increase in supply voltage. So actually, one situation which is good for one VLSI design metric might not be good for the other one. How do we minimize the propagation delay? By reducing the load capacitance, and there are different techniques for that. We can minimize the propagation delay by increasing the width to length ratio of the transistors and by increasing the supply voltage, because we see from this plot that with increasing the supply voltage, our propagation delay decreases. Here is a plot of TPLH versus the width of the PMOS to NMOS transistor widths, and TPHL plotted versus beta, this ratio of the widths of the PMOS and NMOS transistors. Now TPLH decreases with this ratio, however TPHL increases with beta. And from the compound effect of the two, we find the overall propagation delay, and we find that the minimum propagation delay is found at a ratio of 2. So at the widths of the PMOS to NMOS transistors ratio of 2, we find the minimum propagation delay. But we found out from the previous studies, for the optimal threshold voltage, we saw that we need a ratio of 3.5 for the widths of the transistors of the PMOS and NMOS transistors. So basically, one condition is not ideal for all the VLSI design metrics. A ratio of 3.5 was good to achieve the optimal threshold voltage point, but it's not good for propagation delay because we see higher propagation delay at 3.5 ratio. We see a minimum propagation delay at a ratio of the widths of the PMOS and NMOS transistors of 2. So there is always a compromise between the VLSI design matrix. That concludes the lecture for today, and I will see you next time, inshallah.